All right, these are the class notes for section 2.2, day 1. We're going to talk about what it means to be a density curve, and we're going to begin talking about one special type of density curve, normal distribution. So, making some connections here. In chapter 1, we developed a kit of graphical and numerical tools for describing distributions. Now we'll add one more step to the strategy. Okay, when we're exploring quantitative data, you always want to plot your data, make a graph, usually a dot plot, stem plot, histogram. Box plots are pretty common too. Look for overall pattern, shape, center, spread, and for striking departures such as outliers. So that's saying to make sure you address your SOX or your GSOX, depending on which acronym you use. Calculate a numerical summary to briefly describe the center and the spread. And then the new thing is, sometimes the overall pattern of a large number of observations is so regular that we can describe it by a smooth curve. All right, so the general category we're talking about here is a density curve. A density curve is a curve that is always on or above the horizontal axis, or the x-axis traditionally, and has an area of exactly 1 underneath it. A density curve describes the overall pattern of a distribution. The area under the curve and above any interval of values in a horizontal axis is the proportion of all observations that fall in that interval. So that area under the curve, that's going to be kind of a big deal. That's what's going to be driving our thought process through a lot of these problems. Density curves, like distributions, come in many shapes. A density curve is often a good description of the overall pattern of a distribution. Outliers, which are departures from the overall pattern, are not described by the curve. No set of real data is exactly described by a density curve. The curve is an approximation that is easy to use and accurate enough for practical use. So, for a specific example here, the overall pattern of this histogram of the scores of all 947 7th grade students in Gary, Indiana, on the vocabulary part of the Iowa Test of Basic Skills can be described by a smooth curve drawn through the tops of the bars. The shaded area under the curve represents the proportion of students with scores lower than 6.0. This area is 0.293, only 1.010 away from the actual proportion of 0.303. So our estimate based on the curve that a score of 6 falls about the 29th percentile. You can see that areas under curve give good approximations to the actual distribution of the 947 test scores. In practice, it might be easier to use this curve to estimate relative frequencies than to determine the actual proportion of students by counting data values. The median of a density curve is the equal areas point, the point that divides the area under the curve in half. The mean of a density curve is the balance point, at which the curve would balance if it were made of solid material. The median and the mean are the same for a symmetric density curve. They both lie at the center of the curve. The mean of a skewed curve is always pulled away from the median in the direction of the long tail. So if it's perfectly symmetrical, the mean and median are in the same place. As soon as you get a tail, it pulls the mean away from the median. Now that balance point in terms of the visualization, it's not something I'm overly good at. Some students can kind of see that as a visual. If you can, and that's helpful to help locate the mean and the median, by all means do so. Because a density curve is an idealized description of a distribution of data, we distinguish between the mean and standard deviation of the density curve and the mean and standard deviation S sub x computed from actual observations. The usual notation for the mean of a density curve is mu. We write the standard deviation of a density curve as sigma. we can roughly locate the mean of any density curve by I as the balance point. There is no easy way to locate the standard deviation by I for density curves in general. All right, the simplest of all density curves, a uniform distribution. Sally takes the same bus to work every morning. The amount of time in minutes that she has to wait for the bus to arrive is described by the uniform distribution shown. Okay, part A, explain why this curve satisfies the two requirements for a density curve. All right, the two requirements for a density curve are that the entire curve is at or above the x-axis, or the horizontal axis. It is. There's no part of the curve that falls below it. The second condition is that the area under the curve is 1. Well, this is a rectangle. You have rectangle's base times height. The base is 10. The height is 1/10. 10 times a tenth is 1. So both conditions for being a density curve have been met. Part B. On what percent of the days does Sally have to wait more than 8 minutes for the bus? So for these problems, what we're looking at is area under the curve. 8 minutes would be somewhere over here. So more than 8 would be this area. So what is that area? Well, the base is 2. The height is 1/10. 2 times 1/10 is 2/10, or 20%. So on approximately 20% of the days, she's going to have to wait more than 8 minutes for the bus. Part C, on what percent of days does Sally wait between 2.5 and 5.3 minutes? Excuse me. So 2.5, I don't know, roughly about here. 5.3, a little bit past half. What's the area of that rectangle? Well, the base from 2.5 to 5.3, that would be a 2.8 for the length of the base, times 1/10. 1/10 of that, slide that over, about 28% of the time. All right, this one is kind of just an abstract density curve. It's not in the context of anything. It says verify that the graph in figure 2.10 is a valid density curve. So to be a valid density curve, the entire curve has to be at or above the x-axis, which it is. That area has to be exactly 1. So there's a bunch of ways that we could verify that. For the purposes of answering the questions, we're going to answer for the second part of it here. If you go through and find the area of these rectangles, it's 0.2, 0.2, 2, 0.2. You can get the area of that little triangle, 1/2 base times height, 0.05. Get the area of the bigger triangle, do the 1/2 base times height and subtract that off, and you get the 0.15. So the entire curve is at or above the x-axis. If you sum all those numbers up, you get exactly 1. Okay, for each of the following, use the areas under this density curve to find the proportion of observations that are within a given interval. So between 0.6 and 0.8. So between 0.6 and 0.8, that area is 0.2. Okay, between 0 and 0.4 is from here to here. Now we could add up all these individual numbers, but we've already verified, 0.4, I wrote 0.2. We've already figured out that this was 0.4. We've already figured out the whole sum was equal to 1, so that means these guys must have to add up to 0.6. Okay, between 0 and 0.2, between 0 and 0.2, that would be a total area of 0.35. Okay, the median of this density curve is a point between 0.2 and 0.4. Explain why. Well, the median is going to break the data in half. 50% of the data has to be on the left, 50% of the data has to be on the right. Well, counting from this direction, we know that's 20% of the data. That's 20% more of the data, so that's 40%. If we added all of this in here, that would put us up to 65% of the data. So somewhere between here and here, between 40% of the data and 65% of the data, must be the 50% mark. So we know that the median has to lie somewhere between the 0.2 and the 0.4. All right, so one type of density curve would be a uniform distribution. These tend not to be very widespread in terms of having a good application in the real world, so to speak, but it's a nice introductory, simple base times height equals your area, good way to introduce the topic. Here, this is just kind of an abstract version, just to give you the feel for adding areas, so forth and so on, but not very practical. Now we're on to something that's going to be really important to us for a very large chunk of the remainder of the class. One particularly important class of density curves are the normal curves, which describe normal distributions. All normal curves have the same shape. They're symmetric, single-peaked, and bell-shaped. Any specific normal curve is completely described by giving its mean, mu, and its standard deviation, sigma. Right, this formula right here, we're not responsible for in this particular class. We are an algebra-based statistics class, which means that everything that we do in here that involves mathematical computation can be solved using either basic arithmetic or a little bit of algebra. Some of you may go on to heavier, dutier, so to speak, STEM majors in college, in which case the statistics class you take would be calculus-based as opposed to being algebra-based. Those of you that go that route, this is the equation that produces your normal curves. It's just at this stage of the game for us in here, oh look, isn't that cool? There's an equation. We don't really have to do anything with it for the stuff that we do in here. All right, a couple other things we want to mention real quick. The mean is going to be the center of the curve, and the standard deviation turns out to be at the inflection point. And for those of you that are not familiar with that, this part of the curve is concave down. These two parts are concave up. Well, somewhere between being concave down and being concave up, we get what's known as a point of inflection where it changes concavity. In a normal curve, that's going to occur one standard deviation away from the mean in either direction. All right, for this example here, we have two normal curves, curve A and curve B. Which curve has the greater mean? Well, the mean is going to be where is the location of the center line for the graph. So B has a mean of 9, A has a mean of 5, so B has the greater mean. Which curve has a greater standard deviation? The one that's more spread out has the greater standard deviation. The one that's less spread out has the smaller standard deviation. So B, in addition to having a larger mean, has a larger standard deviation as well. Now keep in mind, these are a special case of a density curve, which means the area has to be 1. So if it's going to get taller, it needs to get skinnier in order to keep that area 1. If it's going to get shorter, then it has to get fatter in order to keep that area 1. Okay, a normal distribution is described by a normal density curve. Any particular normal distribution is completely specified by two numbers, its mean and its standard deviation. The mean of a normal distribution is the center of the symmetric normal curve. The standard deviation is the distance from the center to the change of curvature points on either side, meaning the points of inflection. We abbreviate normal distribution with mean mu and standard deviation, capital N, and then we're going to have two numbers in parentheses. The first number represents mean, the second number represents a standard deviation. And we're using population notation here as opposed to sample notation because a normal distribution is describing an entire group of something, an entire population. Okay, why are normal distributions important in statistics? Normal distributions are good descriptions for some distributions of real data. Normal distributions are good approximations for the results of many kinds of chance outcomes, and many statistical inference procedures are based on normal distribution. All of which we're going to look at in great detail over the course of the class. Okay, all normal distributions are the same if we measure units in size of sigma and the mean mu as the center. The standard normal distribution is the normal distribution with a mean 0 and a standard deviation of 1. If a variable has any normal distribution with mean mu and standard deviation sigma, then the standardized variable has a standard normal distribution, mean 0, standard deviation of 1. Okay, we looked at this at the end of chapter 1, or I don't know if it was at the end of chapter 1, at some point in chapter 1. No, we didn't. I apologize. That was chapter 2, when we did data transformation. If you take any set of data and you convert it all to z-scores, that new data set has a mean of 0 and a standard deviation of 1. So normal follows that rule, and it also follows the fact that the original data set is normal, the new data set is normal with those parameters. All right. For any normal curve, whether we're looking at the raw data or we're looking at the standard normal curve after it's been converted into z-scores, they have some properties that are in common. Okay, the 68, 95, 99, 7 rule, that is also known as the empirical rule. Your book refers to it as this. It couldn't be any more awkward to say repeatedly, the 68, 95, 99, 7 rule. The empirical rule is much easier to say. That's what I'm going to refer to it as, but you need to realize they're both the same. Okay, by this rule, 68% of the data falls within one standard deviation of the mean. So the 0 here for the z-score means you're at the mean. You're neither above nor below. One standard deviation in each direction, that's one standard deviation within the mean. That's 68% of the data. If you go 2 standard deviations away from the mean, you're going to capture 95% of the data. Go 3 standard deviations away from the mean, you're going to capture 99.7% of the data, which means at the tails, more than 3 standard deviations in the big direction or in the little direction, you're only looking at 0.15% of the data being more than 3 standard deviations away from the mean. And apparently they're doing some kind of construction right next door for that lovely noise. All right, finish up with a specific example here that ties some of this stuff together. We're going to answer the following questions using the empirical rule, which is also known as the 68, 95, 99, 7 rule. And we're going to do this in a situation where the annual wheat yield per acre on a farm is normally distributed with a mean of 35 bushels and a standard deviation of 8 bushels. Hang on 1 second, we need to find something here off the screen. Got it. Apologize for that. All right, so we have a generic normal curve already sketched for us here. A mean of 35 means that's that center line right there. If it's a standard deviation of 8 bushels, that means one standard deviation to the right represents 43. And that one standard deviation is where we have that point of inflection, where the graph is changing from concave down to concave up. One more standard deviation to the right puts us at 51. One more standard deviation to the right puts us at 59. Okay, going in the other direction, one standard deviation to the left, 35 minus 8 is 27. 27 minus 8 is 19. 19 minus 8 is 11. So by the empirical rule, we know 68% of the data is within one standard deviation of the mean, so that means 34% of it is here, 34% of it's there. And as the next mark, we know that 95% of the data is within two standard deviations of the mean. So 95 minus the 68, and split that up equally, means 13.5% of the data is in here, 13.5% of the data is in there. Then we go 3 standard deviations. That's 99.7% of the data. So subtract off the 95%, split it in half. That leaves you, or gives you, these two like stripes, so to speak. And then 99.7% of the data leaves 0.3% of the data that's split equally on each side. So what percent of the farms yield between 27 and 35 bushels? So between 27 and 35 bushels is 34% of the data. Okay, what percent of farms land between 35 and 51? Well, that would be between here and here. So it would be 34 plus 13.5, 47.5%. What percent of your farms yield between 19 and 43? Well, that's from here all the way to here. So it would be 34 plus 34 plus 13.5. It's 81.5% of the data. What percent of farms yield between 51 and 59? Well, that's there to there, 2.35%. All right, a couple of notes here. This is a very simplistic type of problem where these numbers fall right on a nice clean tick marks. All these boundary points are whole number standard deviations away from the mean in either one or both directions. So if you're dealing with whole standard deviations away from the mean, this empirical rule works just fine. It can give us a good estimation of the particular percentages we're looking for. You're not always going to have nice clean numbers like this. So for example, what if we wanted to know what percent of farms yield between 35 and 52? Well, we can get a real rough estimate in terms of like a lower bound, upper bound, but it's not going to be very accurate. So tomorrow or the next lesson, what we're going to be looking at is, well, what are some ways of getting answers if these numbers don't land right on nice, clean, whole standard deviations away from the mean? Okay, another thing of note here is these questions could have also been phrased in terms of probability. We're not going to be emphasizing that now in Chapter 2, but it's going to become a pretty big deal a little bit later in Chapters 5 and 6, where we're going to get the same basic question, but it'll be worded, what's the probability that if you choose a farm from this population that it has a yield between 27 and 35 bushels? So that area under the curve can be used not only to answer a percentage question, it can be used to answer a probability question. There'd be a 34% chance of that occurring. But as far as today goes, I think that is sufficient in terms of what we need to cover, introducing what it meant to be a density curve, and then introducing one particular density curve that is going to be a pretty big deal to us, and that's the normal curve.